In this video, I introduce a conditional GAN for phase generation. Using phase attributes as extra information to GAN, the generative model can generate specific phases from nothing but random noise. The generator G and the discriminator D place a minimum maximum gain using objective function V, where Y is a phase attribute vector to guide the generative process, and Py is his density model. The actual information Y is added at the beginning of the generator and at the end of the discriminator. The discriminator is used as a classifier to classify if his input sampled from a data distribution or from a model distribution. The generator maps a noise vector from a noise distribution and 36-dimensional phase attribute vector to a new distribution close to the data distribution. Given a mini batch, where n is number of examples in the mini batch, Z is a noise sampled from a noise distribution Pz. The discriminator D maximum the object function JD to distinguish his input from a data distribution or from a model distribution. The generator maximizes the object function JG to train the generator to improve his output. If input sampled from a data distribution, the discriminator will assign a positive label to the data distribution. However, if the input sampled from a model distribution, the discriminator will assign a negative label to the model distribution. At the beginning, because the distribution generated by the generator is not good, so the discriminator is easy to distinguish the samples from a data distribution or from a model distribution. And then we use the difference between the data distribution and the model distribution to define a difference, such as Carroll divergence, moment matching, discrepancy, or worse than distance to train the generator to improve his output, until the discriminator cannot tell the input sampled from a data distribution or model distribution. Namely, the GAN model reaches a Nash equilibrium. Namely, the discriminator always output 0.5 probability, no matter the input sampled from a data distribution or from a model distribution. The discriminator D is a convolutional neural network that uses max out to update the hidden units. And the generator G is a deconvolutional neural network whose inputs are 1D noise vector and 1D phase attribute vector. For example, a deconvolutional layer maps a 1D vector to a 2D feature map. For example, this vector includes two elements. To use a 5x3 kernel, we insert 0 between elements, and then we put 0 paddings. And then we use a 5x3 kernel to generate the new 8x3 feature map. In the code implement, for example, this is a 1D vector include two elements, 2 and 3. And then we use this 5x3 kernel to generate each region for each element. So we have the two, region 1 and region 2. And then we use strata value to determine the overlap region. The training example set of RGB 32x32 phase images. The condition Y is a vector indicating 32 6 face attributes. For example, wear glasses, skin color, age, and smell, etc. For example, this face attribute vector. This one stands for wear glasses. This one indicates a smile face, and this one indicates a man. For more details, please check with these references. Thank you.